Welcome to lecture number 11 for ECE 463 Modern Control, Controllability and Observability. Now the definition of controllability and observability is as follows. Controllability means the ability to drive the system from an arbitrary state to any other arbitrary state in finite time. Observability is the ability to determine the system states from the output and its derivatives. Controllability is important. What controllability means is that you can stabilize the system. It's not sufficient, or it's sufficient but not necessary to be controllable to stabilize it. For example, if the system's open loop stable, you can do nothing and it's stable. But if it is controllable, then it doesn't matter whether the open loop system is stable, unstable, oscillatory, not. I can drive it to any state. I can take a pendulum and drive it up. I can point it down. I can drive it anywhere. Observability will be useful later on when we start building observers. If I can't measure all the states, I try to estimate them. I can only estimate the states if there's information. What observability tells me is that there is enough information in the output to determine what all the states are. So, week 6 to 7, we'll be looking at controllability. In the next couple lectures, we'll be looking at designing feedback controllers to place the poles wherever you want. That's called full state feedback. That only works if the system is controllable. Observability will be used in weeks 8 through 9. It says if a system's observable and I can't measure all the states, I can estimate those states with a state estimator. To do that, we'll be building a full order observer. Again, that only works if the system is observable. So these two things we'll be using again very shortly. Kind of a way to explain observability, controllability is as follows. Jordan form is probably the best of all canonical forms. It's the hardest to get to, but it has the most information. If I take a system like this in Jordan form, meaning the A matrix is diagonal, I could have a system that's controllable, observable. For example, the first state right here is controllable. The input can affect the state x1. Using U, I can drive x1 anywhere. It's observable. From the output, I can tell you what x1 is. So state 1 is both controllable and observable. State 2 is controllable. The input affects it, but it's not observable. From this output, I can't tell what's happening at x2. And any amount of trickery won't work. I can't differentiate it, integrate it, take the frequency content. There is no information about x2 and y. Hence, it's not observable. State 3 is observable, but it's not controllable. That isn't necessarily bad. If this state is stable, I can't do anything about it, but if I can live with it, I can still deal with the system. If the state is unstable, then I'm out of luck. If any state goes to infinity, it'll break your system. The fourth state is neither controllable nor observable. I can't see what's happening, and I can't affect it. Typically, we ignore these states. Again, I can't see them. I can't control them. Sometimes you still might worry about that. If this is unstable, it'll still break the system. What that means is I can't see it from this output, but some other output I can probably see it. I can't control it from this input, but if it's unstable, I got to do something about it. Find a different input. This ain't it. So that's kind of a pictorial example of what is controllable, observable. And that's where Jordan form is really nice. If the B matrix is non-zero, it's controllable. If the C matrix is non-zero, it's observable. Another way to find whether a system's controllable and observable is to look at the transfer function. If I found the transfer function from U to Y in this case, it's a first order system. This is actually a fourth order system. I've got 4 integrators, but the transfer function, only one pole shows up. The fact that I have only one pole in a fourth order system tells me it's either not controllable or not observable or both. If, on the other hand, in contrast, if I have a fourth order system and the transfer function is fourth order, I know all these terms aren't 0 in the B matrix, all the terms aren't 0 in the C matrix. If either one is 0, this pole doesn't show up at the output in the transfer function. So the fact that if I have a fourth order system and a fourth order transfer function, that alone tells me I'm both controllable and observable. Another way to explain controllability, observability, is if a system isn't controllable or observable, I've got pole zero cancellation. Where you put the zero determines whether it's not controllable or not observable. In this case, the pole at -2 cancels. So if I find the transfer function, here's the third order system. The transfer function is only second order, however. Again, this pole can zero cancel. That reduced order tells me it's either not controllable or not observable. If the zero happens before the pole, then this pole is not controllable. No matter what I do to the input, I can't change this pole. If the zero happens after the pole, it's not observable. This pole has an energy state, but I can't see it from this output. So that's kind of one way to think about it. If the zero comes first, it's not controllable. Zero comes second, it's not observable. There's also a matrix called the Controllability Matrix. That's the matrix B, AB, A squared B, and so on. Here's a theorem. If the Controllability Matrix is rank n, then the system's controllable. The proof of that is a little bit easier to see in discrete time. In discrete time, I have x of k plus 1 is ax of k plus bu of k, or zx equals ax plus bu. It's really similar to continuous time, but a little bit easier to see conceptually if I go to discrete time, and the same properties hold. If I can take the input u and drive x to any state in discrete time, then it's controllable. Be analogous to continuous time. So to do that, let's find out what is x at time 4. At time 1, x is equal to x0. At time 0, at time 1, x of 1 is ax of 0 plus bu of 0. X of 2 is ax of 1 plus bu of 1. Substituting for x of 1, I have a squared x0 plus ab u0 plus bu1. X cubed is ax2. Substituting for x2, a4 is ax3. Substituting for x3. Now putting this all together, at time equals 4, x of 4 minus a to the 4th x of 0, bringing that left, is equal to a matrix. That's your b, ab, a squared b, a cubed b, times my input at time 3, time 2, times 1, times 0. If this matrix is invertible, then any state x4 can be obtained just by finding what is the inverse of the controllability matrix times the difference in these two. That'll tell me what my input is. Translating, these are the inputs that can drive me to any state. It's controllable, as long as this matrix is invertible. Now this matrix right here is called the controllability matrix. If I have a fourth order system, then this matrix has to have a rank of 4. If it is, I can solve 4 equations, 4 unknowns. So kind of what that means is that there is some set of inputs that'll drive me from one state at t equals 0 to any state at k equals 4 in 4 samples. Now you might think if the system isn't controllable with only 3 terms, maybe I should try 4 terms, 5 terms, 6 terms. How many terms do I need to find out whether it's controllable or not? This is where the Calley Hamilton Theorem comes to the rescue. You don't have to go out to infinity. What the Calley Hamilton Theorem says is that any matrix satisfies its own characteristic polynomial, meaning the denominator polynomial in a transfer function. For example, here's an A matrix. This is just the 4-stage RC filter from before. If I find its characteristic polynomial, that's the polynomial that has the roots being the eigenvalues of A. There it is. It's 1, 2, 3, 4. X to the 4th plus 7x cubed plus 15x squared plus 10x plus 1 equals 0. Calley Hamilton Theorem says any matrix satisfies its own characteristic polynomial. And you can try that. Here's your characteristic polynomial. If I try it in MATLAB, what is a to the 4th plus 7a cubed plus 15a squared plus 10a plus 1, that's the identity matrix, I get 0. And that's true for any matrix. All matrices satisfy their own characteristic equation. What that means that a to the fourth is linearly dependent upon the previous four terms. A to the fifth is linearly dependent upon these terms as well, as is a to the sixth, a to the seventh, a to the eighth, and so on. So adding any terms past 3 doesn't add any information. They're all linearly dependent. Meaning, when I find the observability matrix, if I have an nth order system, I only need to include n terms. Anything beyond that will be redundant. It won't add to the rank. If it's not full rank for these terms, it won't be full rank if I add any more terms. So you don't have to go out to infinity. If I have a fourth order system, just include 4 terms in the controllability matrix. If that rank is 4, then it's controllable. Observability. You can determine this. Observability means you can determine what the states are just using data from the input, the output, and their derivatives. This is important later on when we start designing state estimators. The observability matrix is defined as follows. It's the C matrix followed by CA, CA squared, and so on, stopping at C to the n minus 1. If that matrix is full rank, if that rank is n, then the system's observable, meaning from that output, I can determine what all the states are just by using the output and its derivatives. If a system is not observable, that means at least one state does not contribute to the output. As a proof, assume a system is fourth order, just for convenience, and assume the input is 0. In that case, I have the following system. X dot equals AX, Y equals CX. Can I determine what X of 0 is from the output and its derivatives? Well, if I take the derivative, that's S times Y, substituting SX equals AX, gives you CAX. S squared Y is CA squared X. S cubed Y is CA cubed X. So if I take the output and its derivatives, that's related to these states, by C, CA, CA squared, CA cubed. If this matrix is invertible, I can determine the states just from the output and its derivatives. It's observable. So that's the condition for observability. The observability matrix needs to be full rank. And again, from the Calley Hamilton Theorem, if I have a fourth order system, I can stop once I get 4 rows. Any additional rows will just be redundant. So there's a couple ways to determine if a matrix is full rank in MATLAB. One is the command rank. This is a built-in function in MATLAB. Just say what is the rank of A, or rank of some matrix. It'll tell you how many linearly independent columns there are. If I have a fourth order system and the controllability matrix has a rank of 4, it's controllable. Again, this is a Boolean test. It either is or it isn't. So for example, suppose the B matrix includes all 4 eigenvectors. If that's the case, then the system is controllable. For example, if I take that heat equation, I found the eigenvector matrix. That's done a screen I didn't show you. And I let B be the sum of all 4 eigenvectors. Then if I find the rank of the controllability matrix, the answer is 4. It is controllable. If, on the other hand, B is only made up of 3 of the eigenvectors, this fourth one is a contribution of 0, now the rank is 3. And also note that the controllability matrix is Boolean. It either is or it isn't. If I take that fourth eigenvector, make it really, really small, from a practical standpoint, it really doesn't have much effect on the states, but this is a Boolean test. It either is or it isn't. It's 0 or it's not 0. If it's not 0, it says it's full rank. That's the problem with the controllability matrix. It tells you controllable, but doesn't tell you how controllable. Second way to determine whether a system's controllable. If all the eigenvalues of the controllability matrix are non-zero, then it's controllable. That's because if all the eigenvalues are non-zero, the matrix is full rank. Let's see. Because the determinant is the product of the eigenvalues, If any of them are 0, the determinant is 0. It also shows up if the eigenvalue is close to 0, then the system is weakly controllable or observable. That's just kind of giving you a warning saying, yes, in theory, I can control that state, but in practice, it's going to be really hard to do anything about it. It's got a very small impact on that state. The determinant is the product of the eigenvalues, so likewise, if the determinant is not 0, the matrix is full rank. If the determinant is close to 0, then it could be weakly controllable. Let's see. And as a sidelight, again, the determinant is the product of the eigenvalues. The trace is the sum of the eigenvalues. Trace is also a function in MATLAB. I have no idea what you do with it, but it's just the sum of the eigenvalues. Kind of interesting, but doesn't tell you a whole lot. So again, let's take that fourth order RC filter. If my B matrix is made up of all 4 eigenvectors, it's full rank. If I find the determinant of the controllability matrix is 27, I can tell you it's not 0, it's full rank, it's controllable. But look at the eigenvalues. Again, they're all fairly far away from 0. This looks like a nice controllable system. If B only contains 3 eigenvectors, the rank is 3, the determinant is 0, and determinant of 0 tells me that it's not full rank, at least one eigenvalue is at 0. If I look at the eigenvalues, I can see that 3 eigenvalues are non-zero, a fourth one is 0. That tells me that one of the modes is not controllable. If I have B is made up of all 4 eigenvectors, but one of them is really, really small, again, the rank test just says, yep, controllable. It's not 0, 0.001 small, but it ain't 0. The determinant gives you more information. Here the determinant is very small. That's kind of a warning, saying that yes, the system's controllable, but you're going to have problems. If I look at the eigenvalues, 3 eigenvalues are fairly large. A fourth one is really, really small. And that tells you that one of these modes is very difficult to control from that input. So this would be a weakly controllable system. Another test. There's a thing called the PBH test. This test says that if the rank of A minus lambda I, B is n for all lambda, the system is controllable. That might seem like a pretty steep requirement since I have to test every possible value of lambda, but it's actually not too bad. A has a rank of 4, or A minus lambda I has a rank of n everywhere except at an eigenvalue. So I only have to test this at the eigenvalues of A. If it turns out that this is equal to n for the ith eigenvalue, then that mode is controllable. If it's not n, then that mode is not controllable. So this is actually kind of more useful. It tells me which modes are not controllable. If there's also a PBH test for observability, if this matrix is equal to n for all lambda, it's observable. Again, I only have to test the eigenvalues. If I plug in an eigenvalue and it's less than n, then that eigenvalue or that mode is not observable. So this tells me which modes are observable and controllable and which modes are not. Tells you a little bit more. A little bit harder to run because I have to run a bunch of tests. Typically what I do is run a controllability test. If it's full rank, you're done. If it's not full rank, I want to know which mode is not controllable or which mode is not observable. Then you run the PBH test. So again, if I take the fourth order system and my B matrix is made up of 3 eigenvectors, I can check, is the rank of A minus lambda I, B equal to 4 at the first eigenvalue? And yep. Second one, yep. Third one, yep. Fourth one, nope. So the fourth mode is not controllable, which I know because I included the first 3 eigenvectors. This also works for the C matrix. If my C matrix is composed of the inverse of the eigenvectors and it contains the first, second, third, but not the fourth eigenvector, the fourth mode is not observable. And again, the PBH test will tell me that. If I find the rank of C, A minus lambda I, at the first eigenvalue, yep, it's observable. Second one, yep. Third one, yep. Fourth one, nope. The fourth mode is not observable. So let's use that for a couple tests. Is a four-stage filter observable and controllable? We're going to have the input coming in on the left, looking at the output on the right. And you kind of know the answer is yes because we've used soldering irons from the base. I can control the tip temperature. Yeah, this probably ought to be controllable. But I can prove that too. Here's the matrix, your A matrix, your B matrix, the C matrix. I'll then run a controllability and observability test for this system. If you do run that test, you'll find out that yes, the controllability matrix is full rank, it is controllable. The observability matrix is full rank, it is observable. Second case, let's look at a cart and pendulum system. Here's the dynamics for the cart and pendulum we looked at previously. This is from the force input, that's the force on the base, and the torque. If you had a little bit of motor right here, applying a torque, this is how the torque would affect the system. Is it controllable from the force? Is it controllable from the torque? Well, if we look at the force input, here's your B matrix. What's the rank of B, AB, A squared B, A cubed B? The rank is 4. Yep, it is controllable, meaning you can balance a yardstick on your hand. And we've done that a couple times, not too surprising. How about the torque input? Is it controllable from the torque input? So to find out, here's my B matrix, the B corresponding to the torque. What's the rank of B, AB, A squared B, A cubed B? The answer is 2. 2 modes are not controllable from the torque input. Turns out these are the poles at 0. And I can find that with the PBH test. Here's your B matrix, here's the eigenvalues of A. Check the first mode, pole at 0. The rank is only 3, not 4. That's not controllable. Second one's not controllable. Third and fourth are. That's these eigenvalues, those eigenvectors can't be controlled. That's position and velocity. If I apply a torque, turning the beam back and forth, I can't have the cart come over and stop it somewhere. So that mode is uncontrollable. I can't control the speed of the cart by twisting the motor at the top. That mode is also uncontrollable. And again, if you think about it, that's not too surprising. Observability. If I just look at the cart position, can I tell you what the cart angle is? Intuitively, I would say no. But if I check the observability matrix, rank of 4, yeah, actually I can tell you the angle just by measuring position. Not really obvious that that works, but the math tells you you can do it. And later on when we build observers, yeah, it does work. You can estimate angle from position. And if you look at the eigenvalues, they're all fairly far from 0. It's not that hard. Kind of what's happening is if you have a cart, as the angle goes back and forth, it causes the position to move back and forth. That's where the information is. And it's not obvious, but the math tells you can do it. If the math tells you can do it, you can probably do it. If I just look at the angle of the beam, is it observable? So if I change the C matrix to 0, 1, 0, 0, just looking at angle, now the rank is 2. The system is not observable from angle. If that's what you're given, you try to build an observer, it ain't going to work. You need a different output. And one candidate would be position. And if I try to find out, if I'm just measuring angle, which modes are observable? Again, it's the first and second mode are not observable. That eigenvector is position velocity. I can't tell you position by monitoring angle. I can't tell you velocity by monitoring angle. So there's where the PBH test kind of comes into play. So in summary, I've got controllability, observability. Controllability is, there's a couple ways to find it. The most common one is the controllability matrix. There's also the PBH test. Let's see, where is it? If the controllability matrix is full rank, the system's controllable. There's also observability. If the observability matrix is full rank, I'm observable. And there's a couple other tests you can run too, like the PBH test, eigenvalues, eigenvectors to tell you if I'm weakly controllable or weakly observable. But this is something we'll be using a little bit later on. That's lecture number 11 for ECE 463, modern control, controllability, and observability.